Hey, it's Colin. I want to walk you through a project that I've been working on for a while now. It's called DarkSafe. So I'm going to step through some of the thought behind it and then some of the code. So my requirements here is first, I wanted the owners to be secret. I also wanted the threshold to be secret too. I also wanted it to be decentralized, so I didn't want to use any trusted off-chain storage party. And I also wanted to see if I could make the owner-to-owner relationship anonymous, where you could just pass signatures between parties and send them to the safe and execute transactions. And this was the most important part for me. I wanted the original signing UX of Ethereum. So some solutions tend to store ephemeral private keys in the browser, and I wanted to keep the normal private key scheme that Ethereum already has, so you can just use all the wallets that you normally do. This is especially important because you'll need to have an admin who sets up the safe initially with all the initial owners based on their addresses or ENS names. I also wanted to take the opportunity to learn some math. So ZK math can be especially gatekeepy, and I wanted to learn something new and be able to break it down for other people too. So I came to this question of, is it possible to have a single data structure which contains but conceals all the signers and the signing threshold? I didn't want to use Merkle trees. I wanted to find a more elegant solution that felt like a little bit nicer than just the tree structure. So the first solution that I came up here with is actually encoding all the valid owner sets and combinations into a polynomial. If you remember the simple quadratic formula where you could say, y equals x squared minus 1, we can go ahead and graph this here. There we go. So this is what a quadratic formula looks like. And every time that you actually pass through the x-axis here, you have like a solution or like a root. So you're saying, hey, when y equals 0, x is going to equal to 1, -1, and +1 over here. And so a polynomial, you have as many curves as there are degrees in the exponent -1. So here we see there's 2, so we see this is x squared, so we have 1 curve here. So if we wanted to draw a polynomial, so here we can see the intersections that we made. So the solutions when y equals 0 is we have, -0.6, and then also we have an intersection at, 0.67, and also an intersection at 1. Now, if you remember, these are called roots of the polynomial when we have these intersections over the x-axis. Okay, now that we're caught up on polynomials, what on earth does that have to do with DarkSafe? If we have a bunch of signers on a safe, Alice, Bob, and Charlie, and it's a 2 out of 3 safe, then we have 3 possible combinations. We have, A plus B, B plus C, and A plus C. So that would represent a valid signer set if their signatures are valid over whatever kind of Ethereum transaction that they want to send on the blockchain. So we forget, but let's remember what an Ethereum address is. This is just the hexadecimal representation of a normal number. If we know these signers beforehand and we can create a combination of all these valid sets before, then we actually know that we can express all of the valid signer combinations as just the expression of a number. Because if maybe Alice's address is, 59 something something something, and Bob's address is just 79 or something like this, we know that we can just add the two together and get 140 or 130. And that represents Alice and Bob. If you see the number 130 out in the wild, you would actually have to factor out all of the additive combinations in order to try to brute force and figure out who is a valid signer on the combination. So in the case of a 20-byte Ethereum address, you would take 20 times 8, so 160. So that means that there are 2 to the 160 possible combinations that you would have to try to factor across to find some of these combinations. My hunch is that this actually isn't secure enough. I think it's fine for a proof of concept and a fun side project, but I'm like 90% sure that you would actually have to hash this value beforehand in order to prevent against some kind of brute force attack. If you know about this, leave a comment. Okay, so we know that if we can simply use addition, we can find out all the possible combination of signers. And so what this table would look like is they would actually end up just being large numbers also encoded as hexadecimal. And now back to polynomials. If these are simply just numbers, we could create a polynomial passes through all these numbers, all these points, when y equals 0. Very simply put, our combinations equal the roots of the polynomial. And so real quickly, you can look this up. There are methods of doing this, but it's called interpolation. So for example, this is a Lagrange interpolation. To show you what this looks like actually in the code, we can go into the scripts file folder and go to the build script. Here we see we get the threshold, we get a safe transaction hash that we want people to sign over. What we do on line 50 is we convert all these signers, all the addresses, into big integers. And then we use an algorithm called kChooseN to derive all the possible combinations of the different address pairs. We're just going to say the roots of the new polynomial will be all those unique combinations. And then we will interpolate a polynomial based upon those roots. Now to show you what this looks like, if we create a 2 of 4 safe and look at the output, we say that these signers yields the following combinations. And so we're going to take those combinations as roots. And then when we interpolate a polynomial that passes through all those roots, this is what it looks like. That's very strange. How is this a polynomial? It's an array with a 1 and then zeros. So array forms are really efficient ways of storing polynomials, and I'll show you why. So as you can see here, we have our exponents above the x variable. And let's fill in this polynomial so it's a little more consistent. 1 times x to the 5th is still x to the 5th. Same with x to the 4th. 0x to the 3 minus 3 plus 0x, which is 0, plus x to the 0 times 1. If you remember, anything to the power of 0 is 1, so 1 times 1 is 1. So now things are really shaping up here. If we assumed that the index of the array was the exponent, and the actual item in the array was the coefficient, we could flip this equation and write this backwards. Positive 1, 0, minus 3, 0, 1, and 1. So to make sense of this code, this polynomial has a degree of 6. So you can write this as x to the 6, and this is the coefficient of x to the 5, the coefficient of x to the 4, 3, 2, 1, and then the leading coefficient. So here's what the setup script generates. It generates a large polynomial that we're going to use. It does a Pedersen hash of the polynomial to store on the smart contract. It also stores the hash of the message, the safe message that we're signing, which is going to be the transaction submitted on Ethereum. And then it also generates the signature data. Concretely, what the Noir circuit is going to do is going to generate a proof for the following. It's going to loop through all the signatures. It's going to derive the Ethereum address. This is similar to EC Recover if you're familiar in Solidity, which gives you the address based on a signature and a hash. Then here we have an intermediary combination variable, which we are going to add to after each iteration in the array. In the case of Bob, Alice, and Charlie, this is the same as adding Bob and Charlie, or Charlie and Bob. It can go either way. It doesn't matter what order they're passed in to the circuit. So if the signatures themselves are valid, which is validated by the circuit, and if the combination set is valid, so if you compute f of x on the combination, you can see this code here in the lib where it multiplies the coefficient by x to the power of the current degree. It should equal 0 to say that it's a valid root, which means that this combination, the signer combination, is valid in the set. And finally, all we have to do is assert that the Pedersen hash is equal to the public polynomial hash. So the only inputs that are public here is the polynomial hash and the safe message hash. So how this works is on chain there will be the safe module called DarkSafe, which is a Zodiac module that exists here. It stores the polynomial hash. So anyone could call the exec function to execute any transaction given a valid proof. How you would execute these transactions is first, you take a safe transaction hash and you sign over that with your private key. You then pass your signed transaction on to the next signer, who will do the same. Eventually, you'll have enough signers. You would go and grab the signer's rotated event that was emitted on chain, which includes the polynomial. You then pass the polynomial and the SIG array into the Noir circuit to generate a proof. All you have to do then is send this proof on chain. The exec function simply takes the proof, generates a safe transaction hash, and by virtue the message hash that you signed. And then all the module requires is that you verify the proof, and then it executes the transaction and sends it on chain. If you're interested, there's an entire end-to-end test here written in Foundry, which sets up the DarkSafe with the polynomial input to set up all the initial owners, ensures that the hash was stored on chain, loads the proof that was generated based on Noir, and then executes a transaction on behalf of the safe where it sends 1 ETH to Alice with the proof, and then passes saying that Alice's balance is now 1 Ether. So from here, I think future improvements could be adding brute force security on the combination list, maybe doing an optimized Merkle tree implementation to see how that looks. I think you could do this exact same thing with KZG, although I'm not sure. So this maybe could be a good project to learn KZG commitments. Also, I wanted to give a big thanks to Tom and Kev from the Noir team. All the work that they did, all the bug fixes and the patches that were required to make this thing work. Also, Colin Roberts and Xerox Jepson for helping me 2 ETHs ago back in Paris mess around with polynomials and figure out a potential data structure that could work. I had a lot of fun with this project and learned a ton along the way. And hopefully this was helpful for those who wanted a bit more math background. I hope maybe some of the polynomial stuff was interesting to those who didn't know. And definitely go check out a project called Dry. It was made by some folks over at ETHCC in Brussels this past summer. It uses a pretty similar circuit, but instead they use Merkle trees instead of polynomials. And they actually store keys in the secure enclave and have a web app. So it's all Face ID based. I'd really recommend checking it out. Great work to the Dry team. Please feel free to mess around on the repository and open up any issues or leave comments. I'd love to work on some of this stuff together. Thanks.